So in section 3.6, we're going to be adding another couple of ways to prove something. Now there's such a subtle difference between these two methods, and so a lot of times people just choose one or the other, but I do want to show you both in case you want to use one as opposed to the other. Alright, so far we've talked about ways to prove statements, and we've talked about this direct proof. Alright, direct proof is just where you assume your hypothesis, you do a lot of work in between, and you conclude with your conclusion. Alright, so we've done that one in prior sections. So now we're going to talk about indirect proof. And an indirect proof, there's two different ways you can do this, and like I said, it's going to be a very subtle difference between the two. We've got a proof by the contrapositive. You probably remember what the contrapositive is, but if not, we're going to remind you on the next couple of slides. And then the second one is what we call a proof by contradiction. And like I said, the difference in these two different kind of proofs is so subtle, but sometimes people prefer one over the other. And sometimes there's advantages to doing a proof by contradiction where you can't do it the exact, same subtle difference way, I'll say, by the contrapositive. So first we say the contrapositive. Alright, so we talked about back in chapter 1 that if you have a conditional statement that it and its contrapositive are logically equivalent. So if one is true, the other is true. If one is false, the other is false. And so back in chapter 1 we talked about the conditional statement that says for all x that's in your domain, if P, then Q. Or another way we would write this is that P implies Q. Now the contrapositive is going to be, again, for all x that's in your domain, if Q of x is false, then P of x is false. And so the way we would write that in sort of a shorthand format, we would say not Q implies not P. Alright, so sometimes if you can't prove this P implies Q very easily, try it this way. Assume not Q and show that that leads to not P. And then because they're logically equivalent, if you've proven one, you've proven the other. Also, if you've shown a counterexample to one, that same counterexample should be able to go for the other one. So let's look at this example. It says you want to prove that for all integers n, if n squared is even, then n is even. And this one's pretty much already written in the if-then kind of format, so we won't have to rewrite this. Alright, so let's get started. We're going to say a proof. And in parentheses, I'm going to say we're proving this by the contrapositive. Alright, so first thing we need to do is, of course, we need to assume what we're given. But then it's a little bit different here because we actually need to think about what the contrapositive would say here. So let's look at this statement that I've just written up here, and I'm just saying that this is going to be our contrapositive here. So let's see if it makes sense. Alright, the first part, for all integers n, that's not going to change. Alright, so basically anything that you're given before the if, you're still going to have that same thing. But it's the if and the then part that will change. Now your contrapositive would say, okay, if n is not even, alright, well if n is not even, that means that n is odd. And then it says then, we want to do not P, and our P was that n squared is even, so we're going to say n squared is odd. Alright, so that would be not the P part. So when I actually try to prove this, I'm going to be proving this statement instead of the one that was originally there. Alright, so let's do our assumption. Alright, we're going to say we're going to assume that n is an integer and we're going to assume that n is odd. Alright, so again, I'm looking at the contrapositive statement and trying to prove that. So we've taken care of this part and we've taken care of this part. Now notice from here really it's just becomes a direct proof. Alright, but we're just proving the contrapositive. Alright, so what do we know if n is odd? Alright, well, we'll say by definition there exists an integer such that n is equal to 2k plus 1. All right, so that's by the definition of odd. And so we're trying to show that n squared is odd, so this is what I'm aiming for right here. All right, my little square kind of got lost in the shuffle here, but that's n squared there. All right, and so we'll just say then n squared is going to be equal to 2k plus 1 squared, which is going to be 4k squared plus 4k plus 1. And again, we're trying to show that this number is odd, so we want to be able to write it as 2 times something plus 1. All right, well, I think you can probably see that that can easily be done here. If we just write in parentheses, let's see, a 2k squared plus 2k, and then the plus 1. We almost have it. The only thing, and we've seen this several times before, the only thing I need to argue is that this indeed is an integer. All right, and I think we can see that by the closure property, since you're just multiplying and adding integers, you will come up with another integer. And the reason you know that is because up here we said that there exists a k that's an integer. All right, so let's write that by the closure property. Um, 2k squared plus 2k is an integer. And so now we have it. The definition of odd says that if you can write an integer, or if you can write, a number as 2 times an integer plus 1, then that number is going to be odd. All right, and so by definition, this n squared, which is equal to this 2 times 2k squared plus 2k plus 1, is an odd number. All right, so what we did was we just finished proving the contrapositive. Now I'm actually going to write that there just for emphasis here that we did prove the contrapositive, and so now we can put our therefore. So we'll say therefore, for all integers, if n squared is even, then n is even. All right, and so we actually proved this by proving the contrapositive, which was so much easier. I didn't really point this out, but if you had tried to do this problem like as it was originally written here, you could assume that n is an integer and assume that n squared is even, but where is that going to take you? So if you said n is an integer and n squared is even, so I'll just say is equal to 2k, how does that lead to this? All right, about the only thing that I can tell you to do to get from maybe the n squared to the n would be to take the square root. So if you take the square root of both sides, you've got that n is equal to the square root of 2 times k. But then you would have to argue that the square root of 2k is an even number, and that might be a little bit hard to do. I won't say it's impossible, but you'd probably get very wordy. You might have to introduce some other notation, and so to me it was just a lot easier to go the other way. So I'm just going to declare this one as hard to do. So one thing I'd say is if you're trying to prove something, you start it like a direct proof because you may not know. Of course, in this section, you'll know that you're supposed to do it this way. But, if you're on a test and you think, okay, let me just try it do directly, if you get stuck, just ask yourself, is it easier to prove the contrapositive? And then try to do that instead. Now, when you're doing a proof by contradiction, what you're going to do here is follow these 3 steps. All right, and again, this is just an indirect proof, the second type. You're going to assume the negation of the statement is true. or in other words, that the original statement is false. Now, one thing that I do want to point out is that you will still assume that you're, looking at for all x in the domain, so it won't be that part is different, and you're also going to assume the if p part, so that's still true. But then what you want to assume is that the q of x is not true. All right, so you're going to be assuming not q. But you're also going to be assuming for all x and d, you're going to be assuming p of x, and you want to assume this. And then what happens when you're actually going through and you're trying to do this as a proof, you're going to show that what you just supposed leads logistically to a contradiction. All right, and so it's kind of like, if a number is, say, greater than 4. Well, if a number is not greater than 4, that means it's less than or equal to 4. And so what you're going to do is you're going to actually contradict one of those, which means that, oh, well, it has to be the other case. All right, so you want to show that this supposition leads logistically to a contradiction. And then you're going to conclude that the original statement to be proved is true. All right, so what you assumed is actually false, and so it must be that the original statement is true. Let's look at this kind of broken down in this form. All right, this is kind of a picture way to look at it. So you were trying to prove that P implies Q here. All right, well, first thing you're going to do is to assume the P. All right, so that's different from our proof by contrapositive. So assume P is true and not Q. All right, and remember, P is the hypothesis, Q is the conclusion. And then what you want to do is to work with your assumptions until you either contradict the hypothesis or you're going to contradict some other well-known proven fact. And that's probably the difference between a proof by contradiction and a proof by the contrapositive. All right, in a contrapositive, you're just showing that not P is true. All right, well, in this particular case, when you're doing contradiction, it could be that you're contradicting the hypothesis, but it also could be that you're contradicting some other well-known proven fact. All right, which if you know that can't happen, then that would lead you to your contradiction. All right, and so then you should have something like P and not P. All right, that may not be very obvious until we see an example. And if you said something like x is less than 4 and x is greater than or equal to 4. All right, well, that would be a contradiction because I know that a number can't be both of those, and so that would say, oh, well, that can't be true. And then you would go back and say, that your original thing you were trying to prove was true. And so this means that not Q is false, and you're going to end with concluding that Q is true after all. All right, so that'll be kind of the steps that we'll take here. So let's look back at this same exact problem that we had before. We want to prove for all integers n, if n squared is even, then n is even. So we're not proving the contrapositive here, but what we'll do is we'll assume that n is an integer, that n is even, or n squared is even. All right, and then this is where you're going to assume the opposite of something. All right, instead of assuming that your n here is even, we're going to assume that that's not true. All right, and so we're going to assume that n, you could say not even, but we'll go ahead and just shortcut it and say, okay, it must be odd. All right, so we got all of these three things that we're assuming. All right, we already said that you can't really get anywhere with the n squared part, but this part that we just assumed that n is odd, we definitely can work with that. So let's say by definition of odd, there exists a k, that's an integer, such that n is equal to 2k plus 1. All right, and so I know that n has to be equal to that. All right, and then this part will look very similar to what we just did. I'm going to look at what n squared happens to be. Alright, and we did this a while ago, and we came out with 2 times a 2k squared plus 2k plus 1. And so what does that mean about n squared? Well, we said a while ago that that means that n squared is odd, and definitely that's true by the definition. This right here is an integer. And so we'll say by definition, or actually by the closure property, we need to say that first. By the closure property, this 2k squared plus 2k is an integer, which means that by definition n squared is going to be an odd number. Oh, but what did we assume in the beginning? Well, we assumed that n squared was even. And so now we've got that n squared is odd, and so there we have our contradiction. All right, and so if you wanted to just go ahead and say which is a contradiction here, that's fine. I'm going to write it out one more step. We're going to say, but n squared is even and odd. Which is a contradiction. Alright, so we had from the beginning that it was even. Now we just showed that it was odd. That's a contradiction, and so that means that that can't really be true. Well, what really can't be true? Alright, well, it was this part right here that we assumed that n was odd, and we just showed that we came up with a contradiction. So what that means is that this thing actually must be true. Alright, so we'll say therefore n is even. Alright, so make sure that you assume everything in your hypothesis, anything that comes before your hypothesis, and then assume the opposite of your conclusion. And then you're going to work with that, and you're going to come up with some contradiction. In this case, notice that we were able to contradict the n squared being even. And so then we had that n squared was even and it was odd, which is a contradiction, and that can't happen. And so therefore we could conclude with what we were trying to show. Alright, let's see one more by contradiction, and I want to do this one in particular because it's not written in that if-then format. But I think you can see that if you're trying to prove that there is no greatest integer, what we would assume is that there is a greatest integer. Alright, so if we're proving this by contradiction, alright, what we'll do is we will assume that there is a greatest integer. Alright, so let's go through and do that. Let's say assume that x is the greatest integer. And so what we want to do is we want to come up with a way to contradict that fact. Okay, so we're assuming that x is the greatest integer, so how can we contradict that? Well, if I can just find an integer that's bigger than this one, then we're good to go. Now there's plenty of ways that you can actually find an integer that's greater than x. Alright, you could multiply x times some integer, you could add an integer, so lots of ways that you could do that here. And so let me just write here that we will show that there is another integer that's going to be greater than x, which will definitely contradict what we just assumed. Alright, well you just pick whatever way you want to do this. So let's say we want to consider, let's say x plus 1. Alright, well is x plus 1 bigger than x? Well sure it is, okay? But the other thing is it an integer? Well sure it is, because if x is an integer, which we said that it was, we said it was the greatest, but when you add 1 to it, that's going to be bigger. All right, and x plus 1 is definitely another integer. That's by the closure property. So by the closure property, x plus 1 is an integer. But also, x plus 1 is greater than x. And so we can say that x plus 1 is a bigger integer than x, which contradicts x being the biggest integer or the greatest integer. And because we got this contradiction, that means that up here when we assume that x is the greatest integer, that wasn't really true. And you could keep doing this, if x plus 1 is the greatest integer, well, you could always add another 1 and another 1 and another 1. And so since you could continue this process, we can just say that, that there is no greatest integer. So I'm going to say, therefore, there is no greatest integer. All right, so we came up with that contradiction, and so what we were trying to prove in the beginning actually is true. So I'd like for you to try these problems here on page 178, and then we can talk about any of these during the next class period. One other thing that I want to point out is that sometimes people like to use, notation, shortcuts, and all that, and that's fine. If you ever want to use something for a contradiction symbol, there's several different ways that you can do it. But one thing that I have seen is to use this symbol here. It looks like 2 parentheses with a little extra line on the left-hand side. And the story goes that there was once a company or a group of people that said, we can take an arrow, or we can make an arrow that is able to penetrate any shield. All right, and so there's no shield that we can't get through. But then that same company also said, oh, we can also make shields that can withstand any arrow. And so you kind of see that this is a contradiction, right? So if you can build an arrow that can penetrate any shield, it should be able to penetrate your shield, but you've just said that your shield can withstand any arrow. And so that is supposedly, where this little symbol for contradiction came from. I've also seen people just put, like a big X at the end or something to say, that's a contradiction, or you can just write it out. So just wanted to point that out in case you like to use shortcuts.